Okay, so carrying on here with some gas law calculations, we want to look at a couple of other ways we can relate the information that's in our ideal gas law. So two of the things that we can start to look at, one is calculating the density of a gas, which would be the mass of a gas sample compared to its volume. Just like we saw for density of solids and liquids back in chapter 1. And we can also start to think about the molar mass of a gas sample, which would be the mass of the gas in the sample compared to how many moles of the gas are present. So both of these will involve incorporating mass into our ideal gas law. So let's start with density. And we already know that we can set PV equal to nRT. But a helpful thing to think about here is if you take the mass of a gas sample, and we would measure mass in grams, and you divide by the molar mass, which is grams per mole, right? This is stacked fractions, so this is maybe a little more complicated than we usually see it, but grams would cancel out here, and moles would come back to the top. So we're more likely to see it like this. We start with a mass, and then we invert the molar mass, like so, to cancel out grams and end up with moles. But this way, right, if we take the mass and divide by the molar mass, that is the same as how many moles of the sample there are. So we can plug mass divided by molar mass in for N back here in our ideal gas law. So that would give us PV equals mass times RT over the molar mass of the gas. Now by putting mass into the ideal gas law, now we can think about things like density, or things like just solving for the molar mass. So if I want the density is, we know, mass over volume. So if I can get the mass on top, the volume of the sample on the bottom, and we can do that by manipulating our gas law here, we can define that in terms of the other properties of the gas. So mass is on top here on the right. That means if I divide both sides by volume, I'd have mass over volume. That will require me to multiply both sides by molar mass. So that would be pressure times molar mass on top. Right? And then I've got to divide both sides by RT. So divided by RT. So the density of a gas is equal to the pressure times the molar mass over RNT. Now, one really useful thing to recognize here, right, at the same pressure and temperature, and we know R is always the same, density and molar mass are going to be related to each other. So at the same pressure and temperature, if the molar mass of the gas goes up, the density of the sample would go up. Molar mass goes down, the density of the sample goes down. So the heavier in terms of molar mass a gas is, the more dense it's going to be at a particular pressure. Okay, now so we could use this and just solve this equation, right? But we can also use this just for relationships. So let's do both here in this problem. We don't really need to do a calculation to answer the question, but we should practice doing this calculation as well. If we're just asked which gas is the most dense at 1 atmosphere and 298 K, right? If they're at the same pressure and the same temperature, the densest gas is going to be the one with the higher molar mass. So CO2, we know carbon's about 12 and oxygen is 16, two of them, so that would be 44.01. N2O, two nitrogens, nitrogen's 14.01, so 2 would be 28.02, plus 16 for the oxygen would be 44.02, so just a little bit more than CO2. But chlorine is 35.45, so Cl2 has a molar mass of 70.90. So the most dense would definitely be the chlorine gas. It's got the highest molar mass of the three we were provided. Now let's go ahead and calculate the density of chlorine anyway. So if we've rearranged our equation here, all we have to do is plug in, just like we've seen with other gas law problems. If the pressure is 1 atmosphere The molar mass of chlorine is 70.90 grams per mole. Gas constant goes on the bottom. And the temperature, and it's already in Kelvin there in the information, 298 K. Now let's look at the units here because it does get a little complicated with stacked fractions, but we have atmospheres there and there, that's going to cancel. Kelvin is there and there, that's going to cancel. And moles is there and there, that's also going to cancel. What we're left with is grams per liter. And that's a good set of units for density. It is mass per unit volume. Right? So you can kind of verify that your equation is set up correctly if the units work out to give you the units you're looking for. So 70.9 divided by 0.0821 divided by 298. So that would be, looks like 3 sig figs. So this is going to be 2.90 if we go to 3 sig figs. Grams per liter. That would be the density of chlorine under these conditions. Now, density of a gas is going to be dependent on the pressure. You increase the pressure, that is actually going to change the density of the gas. You can see that relationship in the equation as well. If the pressure were to go up, this value on this side of the equation will go up. So higher pressure would lead to higher density. Right? Temperature is on the bottom. So if temperature goes up, the density is going to go down. If temperature goes down, the density will go up for a particular gas. Okay, similar idea with molar mass here. Again, if we think about the equation we already have a little bit higher on the page, if I want to isolate molar mass there, mm here on the bottom, I can multiply both sides by molar mass and then divide both sides by PV. The molar mass of a gas is equal to the mass times RT over PV, and that would give me the ability to solve for molar mass. Now, molar mass is also grams per mole, so if you know the mass of the gas sample, you could just solve for moles and then do that extra division. But let's do this practice problem here. It's kind of set up nicely to fit into the equation. So we're going to calculate molar mass of a vapor, so that's just the synonym for gas. In this case, we're given the density. So density is mass and volume, so it's actually two pieces together there of what we're looking for in that equation. Right? 12 degrees C, we turn that to Kelvin, that will give us our temperature. 743 torr, that's our pressure, but we do want to change that to atmospheres because the only other piece we would need there is R. So again, if we've got this equation, we can set up and work through this problem. So let's just plug it in, and then I'll show you another way we can think about this equation if maybe you're not such a fan of rearranging your formulas here. So let's plug all this in. So let's start with the density. 7.135 grams would be on top. 1 liter would be on the bottom, right? And again, you set up your units so that you can understand how they're canceling out. Don't put grams per liter on top here because that will make the stacked fractions even more difficult. Grams per liter like that. R is on top, right? You will have some stacked units here. That's a 1. Liter atmospheres per Kelvin mole. Temperature, so 12 degrees C plus 273 would be 285 Kelvin. And the other piece on the bottom will be the volume. No, we got the volume already, the 1 liter. It's the pressure that we need. So let's turn 743 torr into atmospheres since we are using R. So that would be dividing by 760, since a torr and a millimeter of mercury are the same thing. So 743 divided by 760 is 0.9776 atmospheres. That will also go on the bottom. Okay, and now if we punch all that in, that will give us the molar mass, and we'll look at the units there once we get that final number. Okay, so I punch all that in and I get 170.77. Looks like we're 3 sig figs just about everywhere. So 12 is only 2, but when we change that to Kelvin, it did become 3. So let's call that 171 grams per mole. Now, let's just verify that we do have grams per mole left over. We've got liters here. It's going to cancel with liters there in R. Atmospheres there is going to cancel with the pressure we divided by. Kelvin there and there cancel. So grams on top, moles on the bottom. Which is exactly what we wanted for that particular problem. Okay, so we have this nice formula. We rearrange our P equals nRT like we did there at the top of the page. Right? We can get an equation to use there. Now there is another way to tackle this problem, but let's look at that in the next video.